Hi everyone, and welcome to the first of two videos going through some past paper questions on the topic of shapes of molecules and bond angles. So first thing we need to talk about, all of these things are going to be covalent molecules. There's no point talking about bond angles in ionic substances because the idea of an ionic bond is a bit of a strange one. It's an electrostatic attraction. There's no bond, it's an attraction that acts in all directions, and we've got a giant lattice structure. So the idea of there being different bonds is a bit strange. So this is all going to be talking about covalent compounds here. So what do we actually mean by a covalent bond? A covalent bond is a shared pair of electrons. Okay, it's as simple as that. You could talk about the fact that it's the electrostatic attraction between the electrons and the nuclei of the atoms, but that's all they're going to want. For a 1 mark question, that's the key thing that you need to have. So it then says here, chemists are able to predict the shape of a covalent molecule from the number of electron pairs around the central atom. Okay, if we look at a molecule like this, we're always going to look at the atom that's in the middle and then work out the bond angles around that. So how do they do this then? Well, to be able to work out the bond angles, the first thing we need to know is what electron pairs we've got. Okay, because the idea is that the pairs of electrons within the bonds will repel each other. They're all negatively charged, so they'll repel and they'll try to get as far away from each other as possible. So the first key idea that we can have is pairs of electrons within a molecule will repel each other. Okay. So the idea is that pairs of electrons repel each other, and then the shape of the molecule depends on the number of electron pairs. Okay, the more electron pairs you've got, then the closer they have to be to each other. If you've only got 2 electron pairs, they can be at 180 degrees from each other. If you've got 3, then they can only be at 120 degrees. So the shape of the molecule depends on the number of electron pairs, but it also depends on whether we've got bonding pairs and lone pairs, doesn't it? Because lone pairs will repel more strongly than bonded pairs will, because they're closer to that central atom. They're not being attracted off in 2 different directions. So the shape of the molecule depends on the number of bonded pairs and the number of lone pairs. And again, that's all it wants you to write here. This is a bit of a strange question that students often don't quite know what to put here. But this is the information that we use, right? If we then, it's almost easier to come and do a question where it's asking you for the bond angle and then think about what you've done. So let's do that, and then we'll come back to this question and think about it. So here we've got a molecule, whatever it is. Okay, fine. What on earth is this? I've never seen this in my life, but here it is. It doesn't matter. We can still work out what it is. And it's asking us for 2 different bond angles here. Okay, so we've got the OBO bond angle and then the BOH bond angle. So to work that out, we always look at the element that's in the middle. So if we've got the OBO bond angle, we're going to look at the boron. The boron has got 3 bonded pairs around it. Okay, and then it's just a case of, have you learned what the shapes are for each of the sets of electrons that you've got? If we've got 3 bonded pairs, then they're going to repel each other equally, and the bond angle is going to be 120 degrees. Okay, and you also need to remember what shape it is. Remember, if it's 120 degrees, then it's going to be a trigonal planar shape. Okay, but they're not asking for that here. If we've got BOH, we're going to look at the oxygen. Okay, now the first one, it is 120 degrees, and you can look at it and go, yeah, it looks like 120 degrees, right? That's fine. You look at the BOH bond angle and you think, that's going to be 180 degrees, right? Look at it. No, they deliberately draw it in a way that's going to catch you out. Okay, don't just look at it and go, looks like 180 degrees to me. How we work it out is we look at the bonded pairs of electrons, don't we? Okay, so what electrons pairs have we got around the oxygen? We've got 2 bonded pairs and we've got 2 lone pairs. And then again, it's just a case of, have you learned, if I've got those pairs of electrons, what shape is it going to be? If we have 2 bonded pairs and 2 lone pairs, then we've got 4 pairs of electrons in total. So we'd expect it to be based on a tetrahedral structure. But remember, lone pairs repel more strongly than bonded pairs. So therefore the bond angle is going to be reduced a little bit. If it was tetrahedral, we'd expect the bond angle to be 109.5. Every time we have a lone pair, it reduces the bond angle because it squashes them together, and it reduces it by about 2.5 degrees. So we go down from 109.5 to 107, and then because we've got 2 lone pairs, we're going to take off 2.5 degrees again. So we'd expect it to be 104.5. And you'd have this non-linear shape. Okay, so it definitely is not how they've drawn it here. The hydrogen would be bending again over here somewhere. Okay, but that kind of shows you nicely then what we said here, right? How do we work out the bond angle? Well, we look at how many bonded pairs and lone pairs we've got and use that to match it up to the shape. And the reason we're doing that is because the pairs of electrons repel each other and the lone pairs repel more strongly. Okay, and we could actually add that in. I don't think we'd need to. We could just say here, because the lone pairs repel more strongly. It's not going to do us any harm to add that in. Okay, finally, the last one here says, give an example of a covalent molecule which has all bond angles equal to 90 degrees. Okay, 90 degrees, the only shape that we know of here really that's got a 90-degree bond angle is the octahedral shape. Something that's octahedral is going to be a central atom surrounded by 6 other atoms. It's a bit weird that it's 6 and it's octahedral. But if you imagine you've got your 4 atoms arranged sort of in a square around the central atom, and then 1 at the top and 1 at the bottom, and it creates an octahedral shape because you've got the 8-sided 3D shape. But then again, it's just one that you've learned. Okay, what is the example of an octahedral shape that we know of? The most common one that comes up is sulfur hexafluoride, SF6. Quite a bit of this topic is just, you need to go and practice it. You need to learn the examples, the bond angles and the shapes, and just make sure you've got those in your head. If we carry on, we've got a few more questions here I want to have a look at. So here we've got this example H3NBF3, and it wants us to draw a dot and cross diagram for that. It says label the dative covalent bond, so there's going to be a dative bond somewhere. Show the outer electrons, okay. So we'd need our periodic table probably, so I would have that with you. Most of these, I know what these atoms are. But so we're going to have a nitrogen bonding to 3 hydrogens, and then we're going to have a boron, and I can't draw circles it seems, and the boron's going to be bonding to 3 fluorines. Right, and then we'll start from the outside and work in, because hydrogen's easy, right? These are just going to be ordinary covalent bonds, and the fluorine has 7 in its outer shell, doesn't it? So these are just going to be ordinary covalent bonds as well, just a single bond. Don't forget to put these extra electrons on the fluorine. It's something that I see happening quite a bit. We don't want to just leave it like this. Okay, fluorines should have that outer shell of 8. Hydrogens, remember, only have 2. And then we need to be very careful when we come and do this bond. Okay, we know this must be the dative bond. It does say label it, so let's do that. So the dative covalent bond is going to be here. If it's a dative bond, what does that mean? Well, a dative bond is a covalent bond where both electrons have been donated by the same atom. Okay, which way is it going to be? Well, boron is in group 3 of the periodic table, so it's already got its 3 dots, so it hasn't got any more electrons. They must be coming from the nitrogen. Nitrogen is in group 5, so it should have 5 of its own electrons. Okay, so it's going to be 2 electrons from the nitrogen. So therefore, what symbol do I need to use here? It does matter. Okay, because of the way I've drawn it so far, we've got fluorine that is crosses, and we've got boron that is dots. So therefore, I do not want to use dots here, because as we just said, these electrons are not from the boron, they're from nitrogen. So these are going to have to be 2 crosses, and then it works out that the nitrogen is crosses and the 3 hydrogens are dots. Okay, you could use a third symbol. You could have fluorine as crosses, boron as dots, nitrogen as squares or something. that would be fine. But you don't need to, as long as you alternate, as long as you go crosses, then dots, then crosses, then you're okay. Okay, but if you did put 2 dots here, you would lose a mark, okay, because these electrons need to be from the nitrogen, not from the boron. Of course, you could draw the whole thing with the opposite way around. You know, you could have dots for fluorine, crosses for boron, and so on. That would be fine, as long as it was all completely the other way around. Right, so that's that. Then it's now going to ask us about bond angles. So it's saying the FBF bond angle in BF3 is different from that in this molecule that we've just drawn. Complete the table to predict the bond angles. Okay, well, what's going on in BF3? Let's draw this out. Okay, you might be able to do this in your head, but a good idea is let's draw it and see what it's going to look like. Okay, I would do this on a scrap bit of paper, which I haven't got, but I wouldn't do it in this answer because they're going to think you're trying to answer this question. So I would draw this out on a scrap bit of paper somewhere. It's boron bonding to 3 fluorines. So what are we going to end up with? It's just going to be single bonds. So this is what my BF3 is going to look like. So what have we got? We've just got the 3 bonding pairs. And so therefore, it should be a 120-degree bond angle. Okay, and again, that's just one you need to learn. So this is a terrible diagram, right? It really doesn't look like 120 degrees the way I've drawn it. Okay, but I didn't know it was 120 degrees until I'd drawn it. Okay, so that's our working out. If this was an actual question, get rid of that. We don't want that marked. But we've worked out it's a 120-degree bond angle. What's going on with this molecule that we've drawn here? What we're looking for the FBF, so we're looking for this bond angle. So we're looking at the element that's in the middle, and the boron here has got 4 bonded pairs. Yes, this is a dative bond, but that doesn't make any difference when we come to look at bond angles. It has got 4 covalent bonds around it. So therefore, if it's got 4 bonded pairs, we'd expect it to be tetrahedral and 109.5. Okay, so that's the reason for the difference. Right, then we've got a very similar question, but it's looking at the HNH bond angle. So in NH3, it's 107 degrees. Okay, and they predicted that in this molecule that we drew, it would be a larger bond angle. Explain why they would think this. Okay, well, first of all, we need to explain why this one is 107 degrees. So the HNH bond angle in NH3 is 107 degrees because, and again, we're going to look at the central atom, the nitrogen has, well, 107 degrees is the bond angle we get when we've got 3 bonded pairs and 1 lone pair. And again, that's just something that you need to learn. Okay, we need to be able to match up the bonded pairs of electrons to the bond angles. There's no substitute to that. You just need to write them in a table somewhere and keep looking at it until you've learnt them. So the nitrogen has 3 bonded pairs and 1 lone pair. And so it has 4 pairs of electrons in total, but it doesn't have the same bond angle as tetrahedral because, as we know, the lone pair repels more strongly. So let's write that in. The lone pair repels more strongly than the bonded pairs. Okay, so now let's think about this molecule that we've drawn. And again, we want to look at the nitrogen atom. The nitrogen atom in H3NBF3 has 4 bonded pairs. Okay. So therefore, we would expect it to be tetrahedral again. So we'd expect it to be this 109.5 degrees. Okay, so we're going to get 1 mark here for explaining why this is 107. We're going to get 1 mark for explaining why this is bigger. We might as well actually say what the bond angle is. And then, well, why is it different? Because here you've got the lone pair and the lone pair repels more strongly. That's going to be the 3rd mark.